Hello again. This is the class video that goes with video lecture 17.3, and we're just continuing to talk about interference of sound waves. Okay, so assuming you've already watched lecture 17.3, let's go to the learning objectives for this section and then do an example problem. Okay, objective 1, or 17.3.1. If you have two waves with the same wavelength, beginning in phase from their sources, and they reach a common point by traveling along different paths, then we are to calculate their phase difference phi at that point by relating the path length difference delta L to the wavelength. That sounds more complicated than it is. If you remember from the video lecture 17.3, we're imagining two spherically symmetric sources of sound waves, S1 and S2, or however you want to label them. They're sending out sound waves uniformly in all directions, and the two sources themselves are in phase with each other. So that the sound wave coming out of one, when it's at a pressure maximum, so is the sound wave coming out of the second source, also at a pressure maximum. That's what I mean by in phase. In a different context, what I mean by the sources in phase would be the example I mentioned in the video lecture of making water waves on a pond with two bobbers, or in a ripple tank, going up and down. They're making ripple waves in a water tank. And if the two sources are in phase with each other, then those two little bobbers are going up and down like this, in phase, versus being out of phase with each other, like that. Okay? We're assuming most of the time that the two sources are in phase. Okay? All right. But these waves then are converging onto a particular point in space, a common point. And if they have to travel different distances from their sources to get to that point P, then their waves are going to, in principle, be out of phase with each other. How do you calculate how much phase difference there is? You just need the one key relationship from the previous video. The phase difference between the two waves, that's the phi they're talking about, at point P, divided by 2 pi, is equal to the path length difference, delta L, divided by the wavelength. So if I draw the 2-point sources in an overhead view, S1 and S2, emitting spherically symmetric sound waves in all directions, and then there's the common point P. And straight line distance that the waves have to travel from source 1 to get to P is L1. And the straight line distance that the waves have to travel from source 2 to get to P is L2. And if L1 and L2 are different distances, there is a path length difference, delta L, which is just the absolute value of the difference of those L's. Okay? All right, and the point is a path length difference, delta L, translates into a phase difference, phi, with this formula. Remember, phi is the phase difference in radians, and delta L would be the path length difference in SI, it'd be in meters. That is the key thing to know. 17.3.2. Given the phase difference between the two sound waves with the same amplitude, wavelength, and travel direction, determine the type of interference between the waves, meaning either fully destructive interference, fully constructive interference, or intermediate. Now, really, here's what I recommend you think about with regard to this learning objective. I think it's probably easiest just to think of the condition. There's one condition for fully constructive interference and one condition for fully destructive interference. And it's pretty easy to state the condition in terms of path length difference. Okay? Let me write them down. I wrote this on the video 17.3. For fully constructive interference, you want the path length difference, delta L, to be an integer times the wavelength. M, it's the symbol M stands for any integer in this sequence, 0, 1, 2, ... If the path length difference between the two waves is an integer multiple of the wavelength, then the two waves will be arriving at point P lined up crest to crest, and you'll get fully constructive interference. For fully destructive interference, the condition is that the path length difference between the waves must be m plus 0.5 times lambda, where again m is an integer from that sequence. Okay, m plus a half times lambda. So that means if the path length difference is 1/2 lambda, 3/2 lambda, i.e. 1.5 lambda, 2.5 lambda, 3.5 lambda, then the two waves, when they arrive at point P, will be lined up crest to trough, and you'll get fully destructive interference. Okay? And learning objective 3 there, conferred a phase difference between radians, degrees, and number of wavelengths, is really just referring to using that formula. Okay? All right, let's just go straight to a Wiley Plus homework type problem of interference of sound waves. In fact, I took this one from your book. Oh, let me get that down a little bit so you can see it. Okay? It's problem number 21 in chapter 17. And it reads like this. In this figure, you'll see two loudspeakers, sources of sound waves. You don't have to know anything about loudspeakers other than they produce sound waves. And they're separated by a distance d1 equal to 2 meters. See the distance, the line connecting them there, d1. And they are in phase with each other. That means the sound waves coming out of the two speakers are in phase with each other when they leave their speakers. Assuming the amplitude of the sound waves from the speakers are approximately the same at the listener's ear, and see the listener's ear down there? That's our detector, okay? And that listener's ear, our detector, is at a distance d2, 3.75 meters directly in front of one speaker. Okay, that's the setup. You got two speakers. They're emitting sound waves outward from each that are going outward to the right and spreading out and filling all that air with sound waves. And our detector is a point detector, our ear. That's our point P. Okay? All right. So we know that waves are going to leave the top speaker, let's call that S1, and the straight line distance from S1 to our detector is right there. Let's call that L1. And we're going to have waves leaving the second speaker, that's the second source, let's call that S2. And the straight line distance from that to the listener straight across, L2. So we're setting ourselves up there with our listener, our detector, our ear, to detect interference of those two sound waves. Because there's a path length difference that they travel. L1 and L2 are different. Okay, we are to assume that at any given moment, the speakers are emitting a single frequency sound wave, a sinusoidal sound wave of one frequency. You're used to thinking of speakers with all that rich sound of music that you hear with many, many different frequencies playing all at the same time. No, 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 no. The speaker is emitting a tone, each speaker, a single frequency. Okay? We have equipment in the lab that can do that. Okay? It's emitting a single frequency, each speaker, F. And we're to assume that that frequency can be varied and can be anything in this range. 20 hertz at the low end to 20 kilohertz at the high end, 20,000 hertz. That is the roughly typical audible range for normal human hearing. 20 hertz at the low end to 20,000 hertz at the high end. Question A. what are the three lowest frequencies that give a minimum signal, destructive interference at the listener's ear? And then B, what are the three lowest frequencies that give maximum signal, constructive interference at the listener's ear? Okay? All right. Now, we have D1, 2 meters. We have the distance D2, 3.75 meters. We know that L2 is just D2, 3.75 meters. L1, well, I've just got, I need to know that distance L1. I know this distance along here. That's D1. I know D2. L1 is the hypotenuse of a right triangle. So L1 is the square root of D1 squared plus D2 squared. You could figure out that number. All right, I didn't actually do it, but you can take D1 squared plus D2 squared and take the square root. Okay? All right. Now, in part A, I want to know the three lowest frequencies that give me fully destructive interference at the point where the ear is. Okay? So we want fully destructive interference at point P. I'm going to start with the condition for fully destructive interference that I wrote down in the learning objectives. It's in terms of path length difference. It is the path length difference delta L over the wavelength must equal m plus a half, where m is any element in that string. Okay? If I start with the three lowest m values, okay, then those would be the three lowest values for delta L over lambda that would produce fully destructive interference. So delta L over lambda would be, well, if m is 0, then the right-hand side is a half. Or if m is 1, then the right-hand side is 1.5. Or if m is 2, then the right-hand side is 2.5. And of course it keeps going, but we'll just stop there. Now what I want, though, is the frequencies that correspond to the three lowest frequencies that correspond to fully destructive interference. How do I bring F, frequency, into play here? Well, let's just remember the simple relationship between wavelength, frequency, F, and speed of wave, V. Namely, I'll write it over here to the side. The wavelength equals the speed V divided by the wavelength, by the frequency. And put that in there for the wavelength. Let's see what that looks like then. Delta L over V over F must be 0.5 or 1.5 or 2.5, ... That's the same as, so going down, F delta L over V must equal 0.5 or 1.5 or 2.5, ... Now just solve for F by multiplying both sides by V over delta L, because I want the frequencies that correspond to fully destructive interference. So F equals, so you multiply each of those on the right by V over delta L. So 0.5 times V over delta L, or 1.5 times V over delta L, or 2.5 times V over delta L. But what's the delta L? The path length difference. Then I'm going to write that as L1 minus L2. But L1 was the square root of D1 squared plus D2 squared, and L2 was D2. So that's the symbolic expression for delta L right there. Remember, I know D1 and D2, so it's not a problem figuring out what that is. So I'm going to just plug in numbers now. One thing you might be wondering is, what are we going to put in for the V? Well, the V would be the speed of the sound waves. If a problem in chapter 17 involves sound traveling through air and doesn't mention anything about the speed of the sound, and yet you need that value to solve the problem, like I do here, I need V, you are allowed to go ahead and assume that V is 343 meters per second, the speed of sound in air at room temperature. Please note, though, it's got to be sound in air. And it can't say something, it must be a case where it doesn't say anything else. It doesn't say, oh, and by the way, use V equals 350 meters per second. You see what I'm saying? This problem is it involves sound waves in air. To solve it, I do need to know the V, and it doesn't mention the V explicitly in the wording. That's how I know to use 343 meters per second. Okay, for that then, I'm just going to plug in. I'll do the first one. Let's call this F1 minimum. What do I mean by that? 1, because it's the lowest frequency, and it's going to be a minimum, meaning fully destructive interference. So 0.5 times 343 meters per second over delta L, square root of 2 meters squared plus 3.75 meters squared, square root, minus D2, 3.75 meters. Now do that carefully, do that math carefully, and when you plug that into your calculator, we'll write down what you get. F1 minimum. You'll have a number with unit of inverse second, which is hertz, and to 3 sig figs, it's 347 hertz. That's the first frequency you'll come up. You imagine starting with your speakers emitting at 20 hertz, the low end of that frequency range the problem mentioned, and slowly just increase the frequency being emitted by the speakers. This is the first frequency you'll come to where your observer at point P will say, oh, the volume just went down because they're experiencing fully destructive interference at that location for that frequency, 343 hertz. Now the next frequency at which you'll have fully destructive interference, I'm going to call F2 min. That's 1.5 V over delta L. If you look at that carefully, you'll notice that's just 3 times F1 min. F1 min was 0.5 V over delta L. 1.5 V over delta L is 3 times 0.5 V over delta L. So to get the next frequency for fully destructive interference, F2 min, just take F1 min and multiply it by 3. That would happen at 1029 hertz. That's the next frequency after 343 hertz, where again your listener at point P will say, whoop, the volume just dropped. And what's the next frequency at which you will get fully destructive interference? I'll call it F3 min. Well, that's 2.5 times V over delta L, and that's 5 times F1 min. which is 1,715 hertz. So that would be the next frequency at which your observer at point P would say, whoop, the volume went down. Okay? And you could keep going, right? But it just asked for the 3 lowest frequencies at which our observer would say fully destructive interference is happening. Okay? That's all there is to that. Now, part B wants to know the 3 lowest frequencies that give a maximum signal, fully constructive interference at the listener's ear. So now we want fully constructive interference at point P. So I start with the condition for fully constructive interference written in terms of path length difference and wavelength. Delta L over lambda must equal m, where m is technically any integer in that string, 0, 1, 2, 3, dot, dot, dot. And I'm going to take the 3 lowest ones that are possible. Now, in this case, you got to apply a little bit of physics common sense to the math. I can't include m equals 0 in this string. You see why not? Well, m equals 0 would mean that's a 0 there. That would mean delta L equals 0. That would be 0 path length difference between the 2 waves. That's not possible. Those 2 waves, the one from S1 and the one from S2, are traveling a path length difference, or traveling their respective paths, and the path length difference between them is greater than 0. So it's not physically possible to accept, to take the m equals 0 entry out of that list. You got to apply that physics thinking. Okay? So the 3 lowest m's I can use here are 1 or 2 or 3. And then it would go from there, dot, dot, dot. And now I will bring in frequency, just like I did before. I will replace lambda with V over F. I will then write that as F times delta L over V. And then I will multiply both sides by V over delta L. And I will get expressions for the frequencies that will give me fully constructive interference. The first one will be V over delta L. The next one will be 2V over delta L. The next one will be 3V over delta L, dot, dot, dot. And we just plug in numbers. Okay, I'll do the first one. I'm going to label this first one F1 max, the first frequency at which we'll get fully constructive interference, and it'll be loud. That's V, 343 meters per second, over delta L. Square root of 2 meters squared plus 3.75 meters squared minus 3.75 meters. Again, you get a number with unit 1 over second, hertz, and you get 686 hertz. Okay, so that's the first frequency. Again, you imagine starting with your speakers down at 20 hertz, the low frequency end, slowly ramping the frequency up. When you cross through 343 hertz, you'll hear fully destructive interference. It'll get quiet at the point P. When you get to 686 hertz, it'll be loud, fully constructive interference. When you get to 1029 hertz, it'll be quiet again, the next fully destructive interference. And now I'm going to find the second frequency for fully constructive interference. That's 2V over delta L. That's just 2 times F1 max. right? So that's 1372 hertz. So that's the next frequency at which you'll get fully constructive interference. Then you keep going up and you get to 1715 hertz and you'll get fully destructive interference again. And keep going up and now you'll get to the third frequency for fully constructive interference. And that'll be 3 times F1 max. And that's 2058 hertz. So there are the first 3 frequencies for fully constructive interference. So what I'd like to do is draw kind of a number line, if you like, a frequency line. Let's draw that down here. Going to the right. Frequency in hertz. 0 at the low end. I'll do tick marks off in 100 hertz intervals. 100. 1,000. 15. 2,000. And so forth. Okay? Let's put some of these important frequencies, let's mark them on this number line. Okay? The frequencies for fully destructive and for fully constructive interference. We imagine we start at the low end at about 20 hertz. So we start roughly, each tick mark is 100 hertz, so somewhere roughly right about down there. And we just keep going up beyond to the right end. The first frequency that's important is F1 min at 343 hertz. Oh, just try to get it roughly right. F1 min. That's the first frequency at which our person will say, whoop, it got really quiet. The next important frequency is F1 max at 686 hertz. Let's mark that with green. Oh, roughly there. F1 max. At that frequency, the person at point P will say, oh, it's loud. Fully constructive interference. The next important frequency, F2 min, will be 1029 hertz. Roughly there. The next important frequency will be F2 max, 1372 hertz. Ugh, irritating. $1,372. F2 max. Be loud at that frequency. Then F3 min, 1715. Roughly there. And the last one, F3 max, at least the last one we calculated, 2058. And it would just keep going, the pattern, right? Of alternating frequency for fully destructive, then frequency for fully constructive interference. And in fact, as you can see now, the spacing is the same, uniform. The spacing between any two neighboring values here, like there, is 343 hertz. And it's the same all along. And you're just going to have alternating fully constructive and destructive interference. And that's just from the combining of the two sound waves at the given location. Right? If we picked a different point with a different location, then the frequencies where minimum and maxima would occur would be different. Okay? So it depends on the geometry. Where is the receiver, the listener, the detector relative to the sources? Okay? And then basically apply the conditions for fully constructive and destructive interference. This is a pretty typical homework type problem that involves interference of sound waves. And that's all for this video.